Hey fellas, Seth here, Clan World 0x6. In this edition, it's something no one fucking asked for, but I'm gonna do it, alright? Computing for retards, because for dummies, that's not light enough. I'm gonna make it for real fucking retards. Alright, we're gonna start from the bare basics and just go through pretty much how all of computing works. Alright, we're gonna start low level today. Alright, let's go. Let's jump right into it. 1, 0. Those are numbers. Wow, who would have thunk? That's a 1. That's a 0. What do these mean? These make up binary. What is binary? It's 1s and 0s. There you go, that's binary. It works in a special way. We're not going to go into that right now, but all you need to know is that it's made up by 1s and 0s. But everyone probably already knows that. Anyhow, 1, 0. We can encode information in binary. Alright? You can have 0, 0, 0, 0, 0, 0, 1. 1, 2, 3, 4. That is 1 in binary. Alright? Again, I'm not going to explain why that is 1 in binary. Just know this is 1 in binary. And it's 8 bits. So one binary digit, 1, 1, is called a bit. 8 binary digits is called a byte. This is a byte of information. That is 8 bits. 8 bits equals 1 byte. Okay? 0 is no information. 1 is information. You take these two together and you're able to convey information. Alright? So, yeah, I really need some, like, whiteboard cleaner or something, but yeah. Alright, okay. So, now you know, that's just... And how this works on the low level, which is probably what you're wondering. 0, no pulse. No sign of electricity, basically. I mean, that's technically not true. It's technically low. There is still some electricity, but it's a 0, low. 1 is high. That is a higher amount of electricity. It's it has to do with voltages and stuff, but it doesn't matter. So that's more electricity, that's lower electricity. And that's how it actually looks on the low level. Say this is a wire. Over here, this is our 1. Our 1 is traveling down that wire. It's just electricity. Our 0 is like that. Barely anything. Alright? And so that's how it kind of looks down the wire. It's just a pulse of electricity. Okay. And that's how all data is stored. No matter what, this is how data is stored. It all goes down to a 1 and a 0 in a certain string. Alright. Now, obviously you know what a wire is. Let's go into logic gates, I guess? Yeah, that makes sense. Alright, what is a logic gate? A logic gate, you could think of it as a function, a logical function. Alright, except it's also, well, it's a component made up of other components. It doesn't matter. So let's take our example AND gate. This is an AND gate. It takes 2 inputs. If you don't know what a function is, I think you're too retarded to do this. Basically, just think of it as a box that gives a certain output based on inputs. There you go. So we have these 2 inputs on this AND gate, and we have 1 output. What an AND gate does, you can think all the shit in here, what that is doing. If it gets 2 1 inputs, if it gets 2 of these, it gives a 1 output. If both of these are not 1, it gives nothing. It gives 0. Alright? There you go. Easy. And that is your basic logical gate. You can see how this might work. You make combinations of it with other gates. Let's take another gate. So that's actually the schematic, how you'll see an AND gate on a schematic. I forget what all the other schematic looking gates are. I think OR is like a triangle. Here's OR. If either input is on 1, if either input is 1, it'll give a 1 output. If both of them are 1, it doesn't. That's an OR gate. There you go. So now you can see how if these all give inputs, maybe we could take this AND gate, put it as an input to this OR gate. Yeah, see, so it's called combinational logic. This is how computers work. At the extremely low level, just a fuck ton of logic gates. Fuck ton of them. You hear me? All right. That's at a very low level, but that is pretty much the most essential part to a computer. The fucking logic gates. That's how it does its math. So that's, I could go even more into logic gates because there's a bit more to them, but don't need to. Alright, now let's go a little higher level. Let's look at how a modern computer, or actually let's do a bit more limited computer might work. We have this big box. This box is the CPU. Let's put a CPU. The CPU is the most important part of the computer. This does your math. This takes all these ones and zeros, uses those logic gates from before, and gives out a certain number. It's the brains, all right? So you have a CPU, the base of any computer, does all your math, does all your computing, really. And this CPU is hooked up to other components that kind of facilitate all its operations. It is connected through this thing called a bus. The bus is basically it's a method for transferring this data, our ones and zeros, our electricity, around the computer. So let's say we have this RAM. RAM is random access memory. So this is memory it's memory that will keep its memory until the computer is powered off. Once it's powered off, it forgets everything. All right. And that's used to store information. Kind of. You'll see. But yeah, so we'll have like one bus line. It goes to the RAM. The CPU can talk to this. It can read from it. It could write from it, except that gets into read and write lines. We don't need to get into that now. But yeah, so you can see the CPU's hooked up. So it'll send, let's say we want to load something into a RAM memory address. We do some load command in our machine code. That would, the CPU would know to go, send that to RAM, and do whatever, all right? Then we could have things like, we could have a hard drive. It's just like RAM, it has a read and write line. The CPU knows how to talk to it, it's addressed in its memory. Yeah, shit like that. That's our little computer. So, just the basic idea, we have logic gates in this CPU. They do logical operations that gives us math. We have ones and zeros, which make up every single piece of data for our computer. And we have the CPU talks to other components on the computer through a bus line. All right. Now let's get even higher level, because this is a question a lot of you are probably you tech illiterates out there are probably dying to know. How do we actually program our computer? Now you probably know at a high level how we program our computer. We type our little programming, say it's C, we type our little thing. It's, yeah, there's in C, whoa, that's a number, that's how I program it. Well, that's not how the computer sees it. You see, higher level languages, I mean, C is a pretty low level language, but it's still higher level. These are compiled. What are they compiled into? They're compiled into assembly, ASM. ASM is assembled into machine code. There. We have our C, which gets compiled to assembly, which gets assembled to machine code. The only thing the computer actually understands is machine code. That is, That is the language of the computer. That is the only thing you can talk to the computer in. What's machine code? Ones and zeros. You knew it. And usually represented as hex, but that's a story for another time. Now, so what's so special about this machine code? What's so special about these numbers? It's actually pretty fucking arbitrary. It depends from CPU to CPU, and CPUs implement different architectures, which the basic idea behind that is the way its machine code is formatted, or its commands are different. Say 0, 1, 0 puts a number into memory on this machine code, on this whatever architecture this is. Another computer's architecture, let's say this is a 64-bit architecture, x86_64. Let's say an ARM architecture has it as 1001. See? Now, there's no real reason for this. This is arbitrary. It's just the different ways the CPUs process information. Alright, it's all arbitrary. Machine code is fucking arbitrary. It's just all up to design. But yeah, so your computer understands machine code. It's ones and zeros. Alright. Now you might wonder what this machine code looks like. I'm going to use a hex example because it's just the easiest. Machine code has these things called opcodes. What an opcode is, let's say opcode, it tells the computer what operation you want to do, what function you want to do. What do you want to do this line? All right. So let's say we have load, LD. We want to load some piece of data into somewhere. So we could have load. Let's say load is 0x1. This is hex, but in binary, it's just 0, 0, 0, 0, 0, 0, 1. So hex is pretty easy. I'm going to deal with hex numbers from 1 to 9, so it's easier for you, because hex gets kind of screwy after 9. But yeah, so we have 0x1. This is going to be our load instruction. So when the CPU runs across this instruction, 0x1, it's going to know, hey, I'm going to load it. And that happens through this thing called the decoder. We don't need to get into that yet. Just know 0x1, the CPU will see that and it'll be like, all right, let's load something. So then the next byte of data, this is 1 byte. All hex instructions are 1 byte. 8 bits, 1 byte. All right. The next byte, we might have our the data. Let's say we want... All right, fuck, now I have to explain registers. All right. So you know how you could store information in RAM? All right, you can store a number in RAM. It'll power off once the computer's off. The CPU has its own little storage locations. Yeah, think about that. It has these little boxes, like RAM, and it's called a register. Let's call this R1. And this could store information. Except this is the only way the CPU is actually able to address data. It's the only way the CPU can do math on data. It's the only way the CPU can move data. Yeah, it all works with registers on the CPU. The reason why we use registers, they're super fucking fast, and that's pretty much it. Like, the CPU technically could get the data from there, but it's easier to have it in the CPU, load thing into these box registers, all right? So again, it's as easy. It's a box with data in the CPU, and it's fucking fast, and it's the only way you can work with data. All right, so let's say we want to load something into this register 1. Let's say R1. Yeah, sorry, I'm in a really weird position, so it's kind of hard to write. But we want to load R1. Let's say R1 in hex is like 0x9. That's kind of arbitrary, but whatever. So load R1. What do we want to load into R1? Let's load 5, which would be 0x5. This is 3 bytes of instruction. Now, on most CPUs, it does like fucking magic bit shifting on these. Let's pretend it doesn't. Let's pretend it's retarded. So that what the CPU will do, it'll get this load instruction, it'll get 0x1, it's like, alright, let's load. Then it's going to be R1, alright, I want to load into my register 1. Then it gets the data, it's like, alright, let's put that into register X1. And then we have a number in this register. We can do whatever the fuck we want with this. Usually you'll do math or something with it. We can do add R1 5, and then it'll go, then it'll do all its logic and put R1 into 5. If we put 5 in there and we're adding 5, that'll obviously be 10. We'll have 10 in here. We could do anything with this 10 in this R1. Say we wanted to move it to fucking RAM or something. We do some move commands, whatever. That is fucking unreadable. But yeah, you get the idea. So that is what this hex code, this machine code looks at a low level. That's what it looks like. It's just it's an opcode, arguments. Usually it'll bit shift it. I'm not. It'll take these, do something on it. There you go. That's how it works. Now, what I was writing here is assembly, which is basically one little level up over machine code. There's basically very little difference between assembly and machine code. We use it to make it easier than writing machine code. Like, what's easier to write? 0x1, 0x2, or like load A1. So it's basically the lowest level programming language you'll get, because it is a one-to-one mapping to machine code instructions. Alright? So you could program an assembly all day. That's how most things were programmed until mid-90s, and then most things started moving over to C. But like game consoles, they're all assembly. Early computers, they're all assembly. Yeah, so we were basically talking the lowest level we could, because computers just really weren't that efficient back then. But C is the fucking grand standard now. No one wants to write ASM unless you're making some ROM hack or some game or something for an old system. But yeah. So again, your higher level language, C, it gets compiled down to ASM. We have a thing called a compiler that does that. It basically takes all this input, figures it all out, spits out some ASM. Our assembler takes our ASM, and this is the easier step since it's basically a one-to-one mapping to machine code. The assembler just takes that, spits out some machine code. We can run this machine code on our computer. Alright, so pretty convoluted, but that's how it must be to work with these dumb devices that only understand ones and zeros. Can't wait for quantum computing. It's gonna get fucking wild. Alright, so that was Computing for Retards, episode 1. I might do an episode 2. This is fucking long as shit.